Okay, so in the last class, we looked at how X-rays are being generated. So in this class, we will start to look at how these X-rays interact with a crystal in order to produce an X-ray diffraction pattern from which we then can determine the crystal structure. So first of all, we have to understand here that X-rays interact with the electrons of the atoms within a crystal. So in principle, X-ray diffraction is an elastic scattering of X-rays by electrons. Therefore, to understand X-ray diffraction at crystals, we first need to know a little bit more about how are X-rays scattered by electrons. So let us first look at the case in which an X-ray is scattered by a single electron. Okay, so generally the X-ray scattering occurs because we have a varying electric field in the X-rays that interacts with the electric field associated with the electron. So that leads to X-ray scattering. So J.J. Thomson analyzed the scattering and found the following formula shown here. Okay, and that tells you the intensity of the scattered X-ray based on the intensity of the initial X-ray beam that interacted with the particular electron. Okay, so let us analyze this term here. So the scattered intensity is equal to the original intensity of the X-ray times e to the power of 4, whereby E is the charge of the electron, okay, times R over R0 squared times M squared times Z squared, whereby R0 is nothing else but the distance to the observation point. So that means the distance between the electron and a detector that would measure the intensity of the scattered X-ray. Okay, so now times M squared, whereby M is the mass of the electron, times C to the power of 4, whereby C is the speed of the propagation of the radiation in the vacuum. That is essentially nothing else but the speed of light. Okay, times this term here, 1 plus cosine square 2 theta over 2. Okay, whereby now 2 theta is the angle between the incident direction and the direction where the scattering is observed. Okay, so for instance, if we measured the X-ray intensity directly behind the electron, then 2 theta would be equal to 0. Okay, and 90 degrees would mean that the angle between the observation point and the incident beam would be 90 degrees. Okay, so from this last term here, which contains the cosine term, it becomes clear that the X-ray scattering will be angle dependent. This term here is actually called the polarization, so-called polarization factor. So this means now that the intensity will be a function of 2 theta. So without that polarization factor, the intensity of the scattered X-rays will be equally strong in all directions. Okay, but because of that polarization factor, it is not. In fact, the intensity actually declines with increasing 2 theta value, is indicated here. All right, so this is the interaction between an X-ray and a single electron. Now, in an atom, we have typically not only one electron, unless we have a hydrogen atom, but we have multiple electrons. Okay. So now, what is similar and what is different when we now scatter an X-ray at a multi-electron atom? Okay, so now this is being accounted for by the so-called atomic form factor. So generally, we can say that the scattered intensity is an integer multiple of the number of electrons. Okay, so when we have 2 electrons, then the scattered intensity is 2 times. When we have 4 electrons, then the scattered intensity is 4 times. Okay, so this is, however, only exactly true at a 2 theta value of 0. Okay, so for instance, for a calcium atom, the atomic form factor would be 20 because we have 20 times the scattering of a single electron. If we scattered at a calcium 2+ ion, which has 2 electrons less, well, then the atomic form factor would be 18. Okay, so now you see, however, that the atomic form factor, again, is angle dependent. And in fact, the atomic form factor becomes smaller than the, well, atomic number of the respective atom at which we scatter as we increase the angle. And this is because of interference of the scattered X-rays. So in an atom, the electrons have a distance to each other, which is at the same length scale as the wavelength of the X-rays. Okay? Therefore, an X-ray scattered at electron number 1 and an X-ray scattered at electron number 2 within the same atom will interfere with each other and create an interference phenomenon. Okay, so in other words, there will be a partially destructive interference between the different electrons within the atom, and that actually leads to a decline of the form factor as we increase the scattering angle. Okay. Okay. So now, of course, the form factor will also depend on lambda, because lambda, the wavelength of the X-rays, will determine how these scattered X-rays will actually interfere with each other. All right. So now this leads to a disadvantage of X-ray diffraction over another technique, which is called neutron diffraction. So if we diffract X-rays at a crystal, then that means that the intensity of our measured reflections, as indicated here in a powder X-ray diffraction diagram, will decline with increasing 2 theta angles. Okay, it will actually climb pretty strongly, so that at higher 2 theta angles, our signal to noise ratio will easily become fairly bad, and we will not be able to clearly see our diffraction peaks anymore. Okay, so that can actually be a problem when you want to determine the crystal structure from your X-ray diffraction pattern. So another technique, which is called neutron diffraction, actually does not have this disadvantage. And you see here a neutron diffraction pattern of the same substance. That is because when you scatter neutrons at a crystal, then that is angle independent. Okay, so you can actually collect high intensities at very high 2 theta diffraction angles. So you have a good signal to noise ratio also at high diffraction angles, okay, which is advantageous over X-ray diffraction. So now our standard technique to determine crystal structures is still X-ray diffraction, not neutron diffraction. You can ask yourself why, and the answer is fairly simple. Well, it's much easier to generate X-rays in comparison to neutrons. So for neutrons, you need a nuclear reactor, and we cannot easily produce nuclear reactors in a standard laboratory. Yeah, Thomas raised his hand. What is your question?
Looking at the X-ray diffraction, you mentioned the signal to noise ratio. Is there a general rule or whatever to where you can tell what is still a good peak ratio-wise versus just noise?
No, you cannot. You cannot give you a good rule of thumb here. Usually, at angles up to 40 degrees to theta, assuming that you use copper radiation, you can typically observe good intensities. But as you also see here, from this diffraction pattern, as you go to higher angles, in this case to 65 degrees, the peaks become already pretty small. And if you go to angles higher than 65 degrees, to let's say 80 or 90, then the intensities really become very small. So this here is the typical range here, well, 5 to 65, in which you can still get reasonably high intensities. If you go beyond 65, then it becomes really a lot difficult. So you see here, in the case of the neutron diffraction, you go to 130 degrees and you can still see peaks very clearly.
Okay, thank you.
All right. Okay. Now, we need to go from a single atom to a crystal in which the atoms are periodically arranged. Okay. Now, in principle, we would have to consider the interference of the scattered X-ray, which are scattered at each atom. Okay. So to mathematically handle this becomes very complex. Okay, if you consider X-ray diffraction to be a scattering phenomenon. However, fortunately, there's an easy way out, and that easy way out was found by William H. and William L. Bragg, actually, father and son Bragg, who together discovered what is called the Bragg's law. And according to Bragg's law, you can describe X-ray diffraction through the reflection at lattice planes. So they found that the scattering at a crystal is equal to or equivalent to the reflection at a crystal plane. And reflection at a crystal plane is mathematically orders of magnitudes more simple to handle rather than scattering at a crystal. Okay? So therefore, let us talk now about Bragg's law. From now on, we will always handle X-ray diffraction as a reflection phenomenon at lattice at lattice planes, at crystal planes. Nonetheless, we should not forget that actually we have a scattering phenomenon to consider. Okay, so now crystal planes or lattice planes can be thought simply as planes that contain lattice points and have a periodic distance from each other. Okay, so you see here a generic lattice made of lattice points. Okay, and we can define these three lattice points going through that lattice. So these lattice planes all obey the rules of periodicity. Therefore, they have an equal interplanar distance from each other, which is defined as d subscript HKL. So HKL, as we will learn in a little bit, are so-called Miller indices that define a family of crystal planes. All right. So now, what happens is an X-ray beam interacts with these lattice planes. Now, as I said before, the X-ray beam gets reflected at the lattice planes. Okay, so let us consider an X-ray beam which comes at an incident angle relative to the lattice planes. Okay, so that is our X-ray 1 here, and that is our X-ray 2. So now X-ray 1 gets scattered at the first lattice plane here, and X-ray 2 gets scattered at the second lattice plane. Okay, so now X-ray 2 has to travel a longer path until it's getting reflected in comparison to X-ray number 1. All right, so let's do the reflection. Under the incident angle, which is called theta, and then we will produce this reflected X-ray beam number 1 and this reflected X-ray beam number 2. So now, as I said before, X-ray beam 2 travels a longer path than X-ray beam 1. Okay, now the extent of that path determines how the reflected X-rays interfere with each other. All right, so let us determine how these two X-rays interfere by looking more closely how much longer X-ray number 2 travels in comparison to X-ray number 1. Okay, we can say that in comparison to X-ray number 1, X-ray number 2 travels the path SQ, this path here, plus the distance between this point Q and this point T. Okay, now what can be said about the interference of X-ray number 1 and X-ray number 2? We can say that the interference will only be constructive if that distance plus that distance is an integer multiple of the wavelength lambda. Okay, only under these conditions, this X-ray and that other X-ray will still be in phase. Okay, we can mathematically express this like this here. So we can say that n times lambda, an integer multiple times the X-ray wavelength lambda, is equal to, well, the distance SQ plus the distance QT. Okay, now we can calculate the distance SQ and the distance QT as a function of the interplanar distance d using geometry. And if you do this, we will find that, well, SQ is dHKL times sinus theta, okay, plus dHKL times sinus theta. So SQ certainly has to be the same as QT with regard to length. So we can add these terms up, and then the equation becomes n times lambda is equal to 2 times d times sinus theta. And that is also known as Bragg's law. And it's also known the Bragg reflection condition, okay? So we can only observe a, well, diffraction phenomenon when this condition is fulfilled, okay? When we observe the reflected X-ray under an angle theta that is suitable to fulfill the reflection conditions, okay? So the sinus of that angle theta under which we observe times the interplanar distance of the lattice must be equal times n times lambda. All right. So now this is a great help in order to determine, well, crystal structures from X-ray diffraction phenomena, because we can correlate the angle under which we observe X-ray diffraction to an interplanar distance, okay, which is related to the crystal structure. Okay. But before we go to this, before we discuss it in detail, let us briefly discuss the Miller indices that I already previously mentioned. And I said that the Miller indices define families of crystal planes. Okay, so before we go to the three-dimensional case, let us first understand crystal planes and Miller indices in 2 dimensions. So you see here a 2-dimensional lattice, okay? And you see here multiple unit cells of that 2-dimensional lattice, okay? So now we can think about different families of crystal planes within that 2-dimensional lattice, okay? So you see here one family of crystal planes that have the same interplanar distance d, okay? So now when we look at these, well, crystal planes more closely, then we can see that, well, with respect to the vertical axis, here in b direction, okay, the lattice planes, they are cutting the vertical axis into 2 parts, all right? So we have to go 1/2 of the lattice parameter b until we meet a second crystal plane, and then another 1/2 of the lattice parameter b to meet the next, and then another 1/2, and then another 1/2. Okay, so we can say that these crystal planes cut the lattice parameter 2 into 2 parts. Okay, now when we look into a direction, we see that there's only one part, so we have to go a full lattice parameter a into a direction until we meet the next lattice plane, and then another full lattice parameter, and then another full lattice parameter. Okay, now we can say that these 2 numbers, 2 and 1, defines our family of crystal planes. All right, and we call these 2 numbers the Miller indices 2 and 1 in, well, B and A direction, respectively. Okay? So generally, we can say that crystal planes with the Miller indices HK intersect the unit cell at 1 over H and 1 over K. Okay? So in this case, H would be 2, okay? And we intersect at a half. And K would be 1, so we intersect only at 1. All right? So here's just another example of another family of crystal planes with now a different interplanar distance, okay, which is smaller than the interplanar distance that we saw here. So what is the property of that family of crystal planes? Well, if we go into A direction, then we see, like previously, we have to go a full lattice parameter A until we meet another crystal plane of the family. Okay, but when we go into direction B, we see that we have to go 1/3 of the lattice parameter B, and then another 1/3, and then another 1/3. Okay, so that means that basically our lattice parameter B is cut into 3 parts, 1, 2, and 3. So what would be our Miller indices here that characterize that family of crystal planes? Well, now K would be equal to 3, and H would be equal to 1, okay? All right, now in 3 dimensions, we basically have the same, but we do not have 2 Miller indices, but 3 Miller indices, not only H and K for the lattice parameters A and B, but also L for the lattice parameter C. Okay, so let's practice crystal planes in 3 dimensions a little bit by these 2 simple examples. Now you see here a cubic lattice. And you see here these blue crystal planes in that cubic lattice, and these 3 crystal planes obviously belong to the same family of crystal planes. They have this, they're parallel to each other, and they have the same interplanar distance. Now, what are the associated Miller indices H, K, and L here? So let us define this to be the A direction and this to be the C direction. So now if we go into A direction, we see that we have to go a full lattice parameter until we meet another crystal plane. Therefore, the Miller index will be 1. So H will be 1. Now what about K and L? Now you see that the plane lies actually in the BC plane. Okay, so now according to the definition, the crystal planes with the Miller indices intersect the unit cell at 1 over H and 1 over K, and in 3 dimensions at 1 over L. So now you see that basically we intersect at infinite, right? Because the crystal planes lie in the BC plane. So what number do H, K, and L have to become so that 1 over that number will be infinite? Well, basically, the Miller indices would need to approach 0. We can say that they are 0. Of course, strictly spoken, we cannot divide by 0, but we can divide by extremely close to 0. Okay, so overall, therefore, the Miller indices here would be 1, 0, 0. So now what about this case? So we can first go again into A direction. Okay, and we see again, into A direction, we have to go a full lattice parameter A so that we meet another lattice plane. Okay, so now what about lattice parameter B? So lattice parameter B points this direction. And we see that we have to go, in this case, also a full lattice parameter B into B direction. So therefore, K will also be 1. So now what about L? Well, L is associated with the C direction, and you see that this plane contains the C direction. So therefore, the lattice parameter will be again 0. So overall, that family of lattice planes is associated with similar indices 1, 1, 0. All right. So now different families of lattice planes are associated with different interplanar distances, and there's a geometric relationship between these. There's in fact a geometric relationship between the interplanar distances and the lattice parameters, and we can use this relationship in order to determine lattice parameters from diffraction patterns. Okay, because the angle under which we observe a diffraction is associated with an interplanar distance, which is now associated with the lattice parameter. So let us look at a few examples here. So if we have a cubic cell and look at 1, 1, 0 reflection planes, then the distance between these reflection planes will be equal to the lattice parameter A. Therefore, if you can determine the interplanar distance of the 1, 0, 0 lattice plane, then we know the lattice parameter A. We know the size of the repeating unit in our unit cell. So for the 1, 1, 0 reflection planes, the relationship between the interplanar distance and the unit cell parameter is 1 over the square root of 2. That is because the interplanar distance is equal to half of the face diagonal within a cube. Okay, and when we look at the 1, 1, 1 lattice planes, then the distance between these 1, 1, 1 lattice planes, and one of them you see here, is equal to half of a space diagonal between such within such a cube. Okay, it is equal to A over the square root of 3 to be precise. All right, so now we can develop general relationships for between the lattice parameter and the Miller indices and the interplanar distance associated with these Miller indices for all crystal systems. And we can use these relationships in order to determine unit cell parameters by a process called indexing. Okay, so you see that for the cubic crystal system, the relationship is relatively simple. So 1 over d squared is equal to h squared plus k squared plus l squared times 1 over the lattice parameter a squared. But the more you reduce the symmetry, the more complicated the relationships will get. Okay, you see here the respective formula for the tetragonal case. Here for the orthorhombic case, still relatively simple. But as we remove the 90-degree angle, then it becomes really significantly more complicated. You see here the formula for the monoclinic case, here for the hexagonal case, for the triclinic case, and here for the rhombohedral case. Okay. Therefore, indexing of indexing of unit cells is not as straightforward from an X-ray diffraction pattern. Is not a straightforward process. So unless you have actually a very high symmetry system like a cubic system, you practically cannot do it by hand. You have to use certain computer algorithms that apply these formulas and that apply these formulas to determine the lattice parameters. All right, so I see we still have a little bit time, so I can start with the next presentation already. Which is about reciprocal lattices. So reciprocal lattices are very important because the points of a reciprocal lattice represents, well, the points that define an X-ray diffraction pattern. So the direct relationship between the reciprocal lattice that we see as X-ray diffraction pattern and the real lattice of the crystal. And therefore the reciprocal lattice is also very useful to understand the X-ray diffraction phenomenon and the relationships between this, well, the pattern, the X-ray diffraction pattern, and the actual crystal structure. So now, what is the reciprocal lattice about? So let us build on our knowledge that we have previously acquired about crystal planes that are associated with Miller indices H, K, L. So now each family of crystal planes in real space can be associated with a point in the reciprocal space. And that works the following way. So we can define a vector that points from the origin to the crystal plane, whereby that vector stands perpendicular to that crystal plane, has the length of 1 over d, the interplanar distance between the crystal plane in real space. So that vector defines then a point in the reciprocal space, and we call it reciprocal space because the inverse relationship between the length and the vector and the interplanar distance d in the real space. Okay, so now let's expand on that thought a little bit further. Let us look at this generic lattice here, okay, which has here a unit cell we can define here in origin. Okay, so here we have the unit cell parameter A, and here we have the unit cell parameter B. For simplification reasons, we will again just stay in 2 dimensions here. Okay, then we can define different lattice planes. So for instance, this plane here would belong to a family of lattice planes associated with the Miller indices 0, 1, 0. Okay. So this one here would be associated with the Miller indices 1, 1, 0. This one here would be associated with the mirror planes 2, 1, 0. You see, this one cuts the unit cell parameter in half, yeah, but not the other unit cell parameters. And this one here would be associated with the Miller indices 3, 1, and 0. All right. So now we could define our reciprocal vectors. Okay. So the reciprocal vectors would need to stand perpendicular to these lattice planes. So we can start with this 1, 0, so 0, 1, 0 lattice plane. So our vector would need to start at the origin, 0. So stand perpendicular to our lattice plane and have a length of 1 over the interplanar distance here. Okay, which would be in this case this length. So now, what about the 1, 1, 0 lattice plane? Well, our vector would now need to stand perpendicular to this lattice plane, and the length would be 1 over the interplanar distance between the 1, 1, 0 lattice planes. Okay, so now as the Miller indices increase in comparison to here, the interplanar distance will become naturally smaller. So that means that the vector has to become longer in comparison to this vector. Now we can do this with the other lattice planes that we have considered here as well. So for the 2, 1, 0, our vector would need to stand perpendicular to the 2, 1, 0 here, but be even longer than this one, because the interplanar distance will be even shorter, and the interplanar distance between the 3, 1, 0 lattice planes even shorter than for the 2, 1, 0 lattice planes. Therefore, this vector here will be even longer. Okay, so this vector here would stand perpendicular to this 3, 1, 0 lattice plane. So now you can easily see that these vectors define, well, points in space that define a lattice, okay? And that these lattice points in the reciprocal space would represent lattice points in the, lattice planes in the real space, in the real crystal space. Okay, now a geometric interpretation of the reflection condition using the reciprocal lattice is represented by what is called the Evol sphere, named after Peter Paul Ewald, and is a nice geometric interpretation of the Bragg reflection conditions using the reciprocal lattice. Okay, so previously defined that 1 over d defines, well, the vector sigma HKL. Okay, so remember our Bragg reflection conditions, which said that n times lambda is 2d times sinus theta. So if we define 1 over d to be sigma HKL, then we can rewrite the Bragg reflection condition the following way. Now sigma HKL will be equal to 2 times sinus theta over lambda. Okay. So now we can interpret this form of the reflection condition geometrically using the Evol sphere. And you see the Evol sphere here. So the Evol sphere is a sphere around the center of the real space, where actually our crystal sits, and has a diameter of 2 over lambda. Okay? That is because sigma HKL is proportional to 2 over lambda. Okay, that means that the radius of the sphere is 1 over lambda. Okay, so now we can define the origin of our reciprocal space to be this point here. So we can consider an X-ray beam hitting the crystal. Okay, and at the point where the X-ray beam leaves our Evol sphere, that will be the point of the origin of the reciprocal space. Okay, then any reflection can occur when 2 times sinus theta over lambda is equal to sigma HKL, whereby sigma HKL represents now the distance between the origin of our reciprocal space and a point on the Ewald sphere under an angle 2 theta under which we measure. Okay, so this is nothing else but the Ewald sphere is nothing else but a geometrical interpretation of this formula here. Okay, so we can therefore also say that we can measure a reflection plane being equivalent to a point in the reciprocal space only when this reciprocal point in space lies on the surface of the Ewald sphere, which is now nothing else but, well, the same reflection condition phrased in a geometrical way. Okay, so we can therefore say that we can also mathematically express this by saying, well, this distance here, OP, is equal to sigma HKL. 2 over lambda is 2 times CO, that's the distance between the crystal and the origin of the reciprocal space, times 2, that's the diameter of the Ewald sphere. So therefore, OP has to be equal to 2 times CO times sinus theta. Okay, so in this form, you see actually the geometrical nature of that kind of reflection condition more clearly. All right, so that means now also that, well, as we move our crystal, okay, let's say we rotate our crystal around on our point and having an incident X-ray beam, we will also move around our reciprocal lattice around this point O. Okay, so we will either move the points in the reciprocal space well, into the Ewald sphere or out of the Ewald sphere, and at the point when that reciprocal point lies on the Ewald sphere, then we will actually be able to measure that point in reciprocal space, measure that reflection plane. We will actually observe a reflection in our X-ray diffraction pattern. Okay, let me just very briefly illustrate this here. So we have here our Ewald sphere. So let's say our crystal sits here and our X-ray goes here. Then this will be the origin of our reciprocal space. And you see these red points to be, well, lattice points in the reciprocal space that represent crystal planes in the real space. Now, as we move our crystal planes in the real space, as we rotate our crystal, we will also rotate our, well, reciprocal space. Okay? And whenever, well, a point in the reciprocal space lies on the surface of an Ewald sphere, then we will observe a reflection indicated by these yellow arrows here. So this is actually what we do in a single crystal X-ray diffraction experiment. We move the lattice points in the reciprocal space so that they become lying on the surface of the Ewald sphere so that we can measure their intensity. Because the intensity, the measurement of the intensity will be necessary in order to determine the crystal structure. All right, now you see here two other images. You see that when we actually place a photographic film behind a single crystal, whereby we do not move the crystal in this case, then we see here our diffraction spots. So these diffraction spots can be interpreted as nothing else but lattice points in the reciprocal space. Okay, that becomes now clear when we look at this image here. We have again here our crystal, we have here our Evol sphere, and now some lattice points of our reciprocal space will be, well, on our Ewald sphere. Okay, and these are the points that we will be able to measure on our crystallographic plate, on our photographic plate behind our crystal. All right, so I see we have already spent 2 times more than we should. So let us stop at this point.